We're going to discuss sequences, and I'm sure you've studied sequences in pre-calculus, or and most likely in pre-calculus. A sequence is nothing more than an ordered list of numbers. Now, that list can be finite or infinite, but most likely what we're dealing with are going to be infinite. Okay, so we have an infinite list of numbers, ordered in a particular order. So that's the key word here. And you see that I've made a set of numbers, a list of numbers, 1, 4, 7, 10, 13, and 16. Now, in general, okay, generally, sequence terms are denoted as follows. Okay. Usually we don't actually write out a list like this, but they're noted as follows. Here's what I mean. We have a way to refer to the first element, the first entry, the second entry, the third entry, the fourth entry, and so on. So we'll see something that looks like A subscript 1. I'm just using A's. We could use B's or C's or something else, but it's usually lowercase letters from the first part of the alphabet when we refer to these. And then the second entry is A sub 2. So the index is telling us the position in the list. The third entry, the third number in the list is A sub 3. And of course, if this is a infinite list, okay, infinite sequence, then we'll be out here at some A sub n eventually, and then of course it continues from there. Now, rather than making a list like this, what we'll normally do is we'll write in set notation just A sub n, and that's kind of indicating to us, and some books do, other books don't. We could leave it like that, or we can indicate, oh, n is going from 1 to infinity, and we understand that n is a counting number. We understand that by the way this is working out, okay? Now, even more frequently, what we end up doing is not even writing this way, okay? And maybe let me just reiterate. Remember, A sub 1 indicates that it's the first term. And A sub 2 indicates the 2, that's called the index, indicates we're referring to the second term. And of course, A sub n would indicate that we're referring to the nth term. Now, more likely than not, what's going to really happen is we're going to refer to a sequence by a formula that calculates the particular term we're interested in, calculates the nth term. So sometimes we denote, and most likely we do, sometimes we denote a sequence with a formula. We denote a sequence with a formula for the nth term. Okay. So, for instance, rather than say the sequence of A sub n's, we'll say sequence, or we'll say set notation, 3n minus 2. Now we understand that that's a formula for calculating each of the terms. And so if we want to know the first term, that is when n is equal to 1. So, for the first term, we would calculate, okay, so when n is equal to 1, we would calculate 3 times 1 minus 2. And of course, that gives us a 1. So the first entry in the sequence is 1. And of course, then we would say, oh, if I want to know the second entry in the sequence, that would be when n is 2. So I'd use the formula 3 times 2 minus 2, and that would give me a 4. And we could continue calculating using that formula. And if we do, we'll see that we actually get the sequence that I listed above at the very first time. Okay. Here's another example. We might see n plus 1 divided by n squared. Well, if we want to know the first term, then we would just allow n to be 1. So in this case, when n is equal to 1, then we use our formula 1 plus 1, n plus 1, 1 plus 1 over 1 squared, and of course that's 2 over 1 or just 2. So our first entry is a 2. And then for our second entry, we'd let n be equal to 2. So we get 2 plus 1 over 2 squared, and of course that's simply going to be what, 3/4? 3/4. And then if I wanted n to be, I wanted the third term, I'd have to let n be 3, so that would be 3 plus 1 over 3 squared, which of course is 4/9. And then next, n equal 4, that'd be a 4 plus 1 over 4 squared, and so that would be what, 5/16? And we could even begin to guess now, when we look at some of these previous entries, it looks like the next numerator, see, we had 2 over 1, 3 over 4, 4 over 9, 5 over 16. The numerator is increasing by 1, and the denominator is the next integer squared, isn't it? So we have 4 squared for 16, the next one would be 5, and of course that's where the fifth term anyway, so we'd get 6 over 25. And we could continue, okay? That's not really the big deal here. Okay, in this last sequence, I want to do one more example because this particular sequence is important for us to understand how certain things happen when we get a list of numbers. So with -1 to the power n divided by 2 to the power n, and that's our formula for the sequence. So I'm going to come over here again, and I'm just going to choose n to be equal to 1, so I get my first term. So what I'm trying to do is list several of the terms. So when if my first term is when n is equal to 1, well, that would be a -1 to the power 1 over 2 to the power 1, and of course that's just -1 over 2, or -1/2. Okay. Now when n is equal to 2, that's for the second term, then I'd have -1 to the power 2 over 2 to the power 2. Well, that's 1 over 4, and it's positive. So our next term is positive 1/4. Now, when n is 3, I would have -1 to the power n, 3, divided by 2 to the power n, which is 3, and this time I get a -1 over 8. So my next term is -1/8. Now, what I'm trying to indicate here is that we see an alternating pattern of signs. When n is an odd number, then -1 to a power that is odd gives us a negative result. When n is an even number, so when we're looking for even positions, we have -1 to an even number, which is a positive number. So these are going to continue to alternate from negative to positive, from negative to positive. The next term, when n is 4, we would get a positive 1 over 2 to the 4th, which is 16. And then we'd get a negative 1 over 2 to the 5th, which is 32. And of course, I've kind of run myself into a corner here. We would get a pattern that continues to alternate from negative to positive. And it's because of this -1 to a power, that's what's caused that alternating pattern. That's important for us later on. Now, what we saw on the previous page was called the nth term definition of a sequence. And see, when we see those little formulas, we could have calculated the 100th term. We didn't even need to calculate the 99th term to know what the 100th term is. So we just replace n with a 100. What we're going to do here is talk about, briefly, the recursive definition of a sequence. In the recursive definition of a sequence, we can't necessarily calculate the particular term we want to without some other information. Now, I'm in the habit of calling this a recursive definition, but sometimes books will call it a recursive relation. Okay. Sometimes they just call it a recursive recurrence. Excuse me, a recurrence relation. So use those interchangeably. Well, here's the way that may look. Here's an example of a recurrence relation or recursive definition. Okay, the sequence, let's say this. Let's write the first 5 terms of the sequence of a sub n's where a sub 1 is equal to 25 and a sub n is equal to a sub n minus 1 minus a 5 for n values that are greater than 1. And this is normally the idea, okay, that we have to be given enough information to know at least one term, and it's usually the very first term. So a sub 1 represents the very first term. Okay, so we're going to list that very first term, which is, 25. That's a sub 1. Now, the recursive part, or the recurrence part, says now to find any other terms, we have to have information about a term or terms that precede it. So we can't automatically find out what the 100th term is here, because the formula says a sub n is equal to a sub n minus 1, and then subtract 5. So if we wanted to know the 100th term, that'd be when n is 100, we'd have to know the 99th term, the one right before it, and we don't know that. So we have to do these one at a time starting from the beginning, and that makes it unfriendly, if you will. But anyway, so we're going to use this formula. A sub n is equal to a sub n minus 1 subtract 5. And we want the second term, so that's when n is equal to 2. Well, then according to the formula, a sub 2 is equal to a sub, now n is 2, so that would be 2 minus 1, or a sub 1. See, n minus 1 is right before n. So we would calculate using, to know a sub 2, we'd have to know a sub 1, which of course is 25, and we'd subtract 5 from that, and we would get a 20. So the second term is 20 here. Now, if we want to know the third term, this is a pretty easy one to figure out. If we wanted to know the third term, that would be a sub 3. But to calculate a sub 3, we have to know the term right before it, the term that is 3 minus 1. Okay, well, 3 minus 1 is 2, the second term. So a sub 3 is a sub 2 minus 5. And of course, we already know that a sub 2 from previously is a 20, and so we subtract 5, and of course that gives us a 15. So the third term is 15. And very quickly you can imagine that a sub 4 would be a sub 4 would be equal to a sub 3 minus 5. So we go back over here and we look at to see what a sub 3 is. Oh, it's 15, and so we subtract 5 from that and we get a 10. Now, once we've seen several of these terms, and probably before now, you can see a pattern that's going to start occurring. The next one will be 5 less, the next one will be 5 less, the next one will be 5 less, and we could continue. Now, we were just asked for the first 5 terms, wouldn't we? So I've kind of overdone it. But that's the idea of a recurrence relation or a recursive definition. It means to find a particular term, we have to know something about terms that precede it so that we can finish things out. Now, we're going to change the discussion. I'm not, as you can see, I'm not spending a lot of time here worrying about these ideas of sequences. We're worried about the calculus involved now. So the very first thing we consider calculus-wise when we're dealing with sequences is the limit of a sequence. The limit of a sequence. So if we're given a sequence, so given the sequence, I'm not going to spend a lot of time actually trying to define it. Well, I should say that. But given the sequence, in this case, a sub n, which is actually given by the formula. I probably should have put the formula in here. It's 1 over n. Okay, so if we were listing these, the first term would be 1 over 1. The second term would be 1 over 2. The third term would be 1 over 3. The fourth term is 1 over 4, and so on, and it's going to continue in that fashion, isn't it? Okay, it's going to continue in that fashion. So if we want to know the limit of the sequence, then that's exactly what we write is this fashion. What's the limit of a sub n as n approaches infinity? What we're wanting to know is what number are those, if any, what number, if any, are those terms getting closer and closer to as we go further and further out in the sequence. So in this case, it's a simple question of what is the limit of 1 over n. That's what we're looking at. Each one of these is calculated as 1 over n, but n is going to infinity. And we're pretty familiar and know already that that limit should be 0. And that's in fact the case here. So the limit of a sequence in terms of gut feelings, not being precise mathematically, I think is not such a far reach for us. Now, what I'm going to do following here is to write down some theorems that we just are going to need to be able to use and refer to later on. And I'm going to continue this on the next page. Okay, so let's assume we're given a sequence, and let's assume that we're considering the limit of that sequence. If the limit of the sequence, that is, the limit of the a sub n's as n approaches infinity, exists and is finite, then we say that the sequence converges. So a convergent sequence is one in which the limit of the terms is finite. On the other hand, if the limit of the terms as n approaches infinity doesn't exist or is infinite, positive infinity or negative infinity, then we say the sequence diverges. So a divergent sequence is one in which the limit of the terms doesn't exist or is infinite. Okay, so a couple of examples real quickly. Let's look at the example of a sub n's, which is actually given by this formula. I'll keep jumping back to that, of 1 over n's. This converges, we saw it a while ago, this converges since the limit of 1 over n as n approaches infinity is equal to 0. That is finite, of course, and of course that limit exists. On the other hand, if we look at the sequence of b sub n's that is defined this way, okay, a term is determined by taking -1 and raising it to the nth power, okay, if we're talking about the nth term, and that's times the fraction n times n plus 1, all divided by 2. Well, this might be a little bit difficult, and we're going to talk about some things here in a moment that will help us deal with this. But when we look at the limit of those b sub n's, see, when we're considering the limit of those b sub n's, the real issue is we've got positive, negative, positive, negative, positive, negative. Let's just write down a few terms in this case and see what this looks like. When n is 1, we have negative 1 to the first power, which is negative, and then we have times the fraction 1 times 1 plus 1. So that's actually 2 over 2, so that's the very first term is negative 1, I believe. Now when n is 2, then we have negative 1 to the second power, which will be positive. And then when n is 2, we'll have 2 times 2 plus 1 over 2, which will actually just be a 3, I believe. Now when n is 3, we'll have a negative 1 to the third power, so that's going to be negative. But we'll have 3 times 3 plus 1, what is that, 12 over 2, which is 6. And then when n is, maybe I can now even look at this and say, oh, why was I so silly about this? But let's do one more term here. The fourth term, when n is 4, the negative 1 to the fourth power is positive. And then we have 4 times 5 over 2, which is 10, isn't it? And we might be able to actually get a few more in here and look at the pattern. But the big deal is this number, as n goes to infinity, is just getting larger, isn't it? The numerator is getting larger, but we're always dividing by 2. And so whether we're positive or negative, that fraction is getting bigger and bigger and bigger, isn't it? So this actually diverges. And in this case, the limit doesn't exist at all, okay? It diverges. Since the limit of b sub n's, I don't want to write all that in there, does not exist. It's not even infinite. Okay, so we already know a couple of examples. Rather than try to squeeze this in, I'm going to move on to the next page. This is an important theorem. The theorem states that, let's assume we're given a sequence a sub n, and either we're given a function or we can find a function f for which, for every integer n, if we put that integer into the function, we get the same. In other words, if we put 1 into the function, f of 1 is a sub 1. If we put a 10 into the function, f of 10 is equal to a sub 10, the 10th term of the sequence, and so on, for every positive integer. Well, then if that's the case, the limit of that if the limit of that function as x approaches infinity is equal to L, then we know the limit of the sequence is also equal to L. And you may think, oh, what in the world is this even saying? Or why am I even worried about it? Well, really, so far, when we're talking about a sequence, it's more discrete. It's not continuous numbers. I mean, we're talking about the limit as particular numbers, and we don't have this whole pattern of continuity between these. If we graph a sequence, we'll only have one point at each integer value of x, okay? Say only 1 point for each integer value. So we don't have a point for a 1/2, okay? So, but we are even thinking of it this way. Here's the critical part of this, you know, why I'm even bringing this up. This says we can use, let me write it down. So as I was saying, the significance of this is it really tells us, it says that we can use exactly the same techniques for finding limits of sequences as what we've done in the past for finding limits of functions, because we can treat it like we were finding the limit of the function. So just as an example, the idea a while ago that we had this sequence of a sub n's, like this, that's our sequence. Well, we would define, we would make up the function. We would define the x that we're into, the function that we're interested in, as 1 over x. And so what we see is, of course, f of 2 is 1/2, f of 3 is 1/3, f of 4 is 1/4. And so now if we wanted to find the limit of 1 sub n as n approaches infinity, which we had no trouble with, but later on we may need some other tools, that would be exactly what the limit of our f of x is. See, 1 over x as x approaches infinity. And of course we knew that was going to be 0 anyway, but what I'm referring to is we could use tools like we used before. For instance, L'Hopital's rule. See, we could use L'Hopital's rule, so it becomes very useful. Now, the properties of limits are intact. Let me write this down also. By the way, this is important because that theorem's important because what it says. Now, the properties of limits of functions are intact for limits of sequences. In other words, the limits of sequence properties mirror that of the limits of functions. For instance, the limit of a sum or difference of entries from different sequences, so we're talking about adding basically sequences together here. If we add term by term, the limit of the sum or differences of terms of two sequences is simply the limit of the terms of the first sequence plus or minus appropriately the limit of the terms of the second sequence. Looks very normal, doesn't it? The second property, the limit of a constant times the terms of and that constant is the same constant all the way through, so the limit of a constant times the terms of a sequence is the constant times the limit of the terms of the sequence. So we can factor that constant out. Number 3, this one we probably will use quite frequently. The limit of a product of the terms of two sequences. So we've got two sequences, and we're looking at multiplying the first terms together, looking at multiplying the second terms together, the third terms together, and so on. And we want to know the limit of the new sequence that gives us. All it boils down to is that we find the limit of each of those sequences separately and multiply those two results together. Now this is assuming the limits exist. I haven't said that, but it's assuming the limits exist. So the limit of the product is the product of the limits. Well, that's pretty handy. Similarly, for quotients, the limit of a quotient of the terms of two sequences. So we've got two sequences again, and if we create a brand new sequence where we take the first terms and divide, the second terms and divide, third terms and divide, and so on, then the limit of that new sequence is calculated by, oops, I did a poor job there, is calculated by taking the limit of the, as n approaches infinity, I really bungled this, the limit of the first sequence, that's the sequence made up of the numerators make up, and divided by the limit of the sequence that makes up the denominators. And I need an n approaches infinity above as well. And of course this is provided limits make sense, that the limits exist, and furthermore that the limit of the bottom sequence, of course, is not 0. Otherwise, that wouldn't make any sense at all. And I guess for the record, let me put one more in here that we certainly could use. The limit of the terms of a sequence that are raised to some constant power. Every term is raised to some constant power. Well, that's the same thing as finding the limit of the sequence and raising the limit of the we do this naturally anyway. We don't even realize we're doing it, but when we calculate limits, that's what we're doing. And now that's provided, once again, the limits appropriately exist, and the a sub n's are greater than or equal to 0, so we wouldn't have something like a power of 1/2 and get the power of 1/2 on a negative number, which would be a complex number. So we will use use some or all of these properties of limits of sequences at one time or another? So here's another important theorem. And it says, okay, now we've got a sequence made up of a sub n's. If the limit of the absolute value of the terms of that sequence is equal to 0, of course that's as n goes to infinity, then the limit of the sequence is also 0. Now this is misused a lot of times. Let me point out, this is misused many times because for this to be true, to hold the limit of the absolute value of a sub n as n approaches infinity must be 0, not any other number. In other words, if the limit of the absolute values of the a sub n's is equal to 1, that doesn't mean the limit of the a sub n's is 1. This only applies if the limit of the absolute values is 0, and then the limit of the a sub n's is also 0. So, as an example, if we were given the sequence of a sub n's that looked like -1 to the power n divided by n, because that's what we were given. So that means a sub n is the fraction -1 to the power n divided by n. Well, that may be a little bit difficult to determine, if you will, just a little example, determine, if you will, what that limit is. Maybe not, but here's the thing that we could note in this case. Here's the theorem. This is what's important to remember, is when does it apply? Okay, don't make it apply in places that it doesn't. Here's an example of how it might apply. Is that the absolute value of a sub n is always going to give a positive result, isn't it? And so we know if a sub n is -1 to a power n, then sometimes that's positive, sometimes that's negative, but in this case it will always give us 1 over n. So now we know that the limit of the absolute value of a sub n's is the same as the limit of 1 over n as n approaches infinity, and we know that's equal to 0. So therefore we can conclude that the limit of the a sub n's, the limit of a sub n is equal to 0 as n approaches infinity. And of course the a sub n was -1 to the power n divided by n as n approaches infinity. So we know that limit is also equal to 0. Okay, here's another theorem, another important theorem. Okay, this theorem is called the squeeze theorem for sequences, and in Calculus 1 you talk about the squeeze theorem for functions. This basically says we have two sequences, an a sub n and a b sub n sequence. We have a third sequence where every term in the third sequence is between the corresponding terms of the two sequences. In other words, we look at the fifth terms, okay, then the fifth term of the fifth term of C is a number that's between the fifth term of A and the fifth term of B. Always in this relationship. At least for when we go far enough out that's the case. Eventually that's always true. That's what the rest of that says. For lowercase n greater than capital N, where capital N is some positive integer, and it means eventually. It may not be true for the first 10 terms, but beyond the 10th term, it's always true, as an example. Okay, if the limit of a sub n sequence is equal to the same as the limit of the b sub n sequence, and that's equal to L, then the limit of the c sub n sequence also has to be L. And after all, the c's are always between the a's and b's, and if the a's and b's are getting closer and closer to some number L, then the c's are squeezed in between. They would have to also get close to that same L, wouldn't they? So that's called the squeeze theorem. and I'll show you later how we apply that in a particular example or two. Now here's a theorem that takes a little bit to prove, and I'm not interested in the proofs of these for now. I just want you to believe it and be able to be prepared to use it later on. If we have a sequence that's made up of some constant to the power n, then that sequence converges if that constant r is a number that is between -1 and +1, but not ever equal to -1. It could be equal to 1. Okay, so it converges for those types of r values. If r is a number, so for instance, if we looked at the sequence of 1/2 to the power n, the r in this case is 1/2, and that 1/2 value, that r value, is between -1 and 1, so this converges. Okay, on the other hand, the sequence diverges for all other values of r. So if r is bigger than 1 or less than or equal to -1, then it will diverge. So for instance, if we looked at the sequence of 2 to the n, in this case the r is 2, and that's bigger than 1, so this diverges. You don't have to think much about it. Now furthermore, if it converges, it tells us exactly what it converges to. That is, if we have an appropriate r that's between -1 and +1, but not equal to -1, could be equal to 1. In that case, if we look at the limit, it will be 0. The limit of the sequence will be 0 as long as the r is strictly between -1 and +1. It would be equal to 1 if the r value is 1. I mean, if r value is 1, we have 1 to the nth. And so no matter what n is, we have 1, 1, 1, 1, 1. And of course, the limit of 1 over and over and over is just 1. That's not very interesting. It's really this case that we're most interested in. So up above, when we look right here, our r is 1/2, r to the nth power. So we know it converges, and this furthermore tells us that it converges to 0. That's the only choice. It converges to 0, or in one special case to 1. All other times it diverges because that's different values of r. Well, again, we will use that throughout this chapter. Well, what I'd like to do next is apply the things that we've talked about. That how do we find the limit of a sequence? Well, we can employ all the tools that we have for finding the limits of functions. And then we have some of these special theorems about the limit. If the limit of the absolute value is 0, then the limit of the sequence is 0. We have the squeeze theorem, and then we also have what we just looked at right here. Okay, so we'll employ these properties of sequences, of limits of sequences, and these other theorems to calculate some limits of sequences. And we'll begin that on the next page. I've got several of these to do. And anyway, I've got several of these to do. So let's begin. And here's the problem, the statement. Determine if the following sequences converge or diverge. If the sequence converges, then determine its limit. And we kind of do that when we decide whether it converges or diverges. So what we're after is to find the limit of a sub n as n approaches infinity. And so that's really in this particular sequence, that's finding the limit of the expression 3x squared minus 1 over 10n plus 5n squared as n approaches infinity. Now, a lot of this is just kind of remembering some of our limit techniques. And there's more than one way that we could deal with this, but the way we started this probably in Calculus 1 is we looked at this rational function and we ended up deciding, well, what's the highest power of n in the denominator? It was x's then, but we're dealing with n's that are distinct positive integers. it's n squared. And so what we ended up doing, remember, is multiplying the numerator and denominator by 1 over n squared, or dividing both numerator and denominator by n squared. And so when we do that, we end up with a 3n squared over n squared, which is 3, minus a 1 over n squared for our numerator. And then in our denominator, we'll have a 10n over n squared, which simplifies to 10 over n, plus 5n squared over n squared, which just simplifies to a 5. And then we can easily determine that limit, because the limit of 1 over n squared goes to 0 as n goes to infinity, and 10 over n goes to 0 as n goes to infinity. So the limit we get here is 3 minus 0 over 0 plus 5, which of course is 3/5. So it converges, and it converges to 3/5, doesn't it? That wasn't too bad. Okay, well, let's look at number 2 then. E to the power 2 to the n divided by n. That is our sequence. And we can find the different terms, but that's our sequence. And we want to know if it converges or diverges. Okay, well, here's what I would do. The limit as n approaches infinity of the terms e to the power 2n over n. Now, in this case, notice in this case, I'm going to come way over here. In this case, the limit of e to the 2n as n goes to infinity is itself infinity, isn't it? And the limit of n as n goes to infinity, that's the limit of the denominator as n goes to infinity, is also infinity. And this is an indeterminate form, isn't it? Okay, this is an indeterminate form. And it's of the indeterminate form of the type that L'Hopital's rule applies to. So we're going to apply L'Hopital's rule to find this limit. And I put a little h there for we're applying L'Hopital's rule, if you haven't had me for Calculus 1. Well, what does L'Hopital's rule say? If we have the indeterminate form infinity over infinity, then we can calculate the limit of, the way we calculate the limit is we take the derivative of the numerator and then divide by the limit, the derivative of the denominator, and we then find the limit of that new fraction. Okay, well, the derivative of e to the 2n as n, the derivative of e to the 2n with respect to n, well, it's e to the same power, but then it's times the derivative of the power, which would be 2. So when we take that derivative, we get e to the power, 2 times e to the power 2n. My bad. Now the derivative of n, that is the denominator with respect to n, is just 1. And so now we can calculate that limit because the numerator is getting infinitely large as n goes to infinity, but the denominator is just 1. In other words, we can just simplify it as 2 times e to the 2n and take that limit. And of course, that limit is infinity. And so that says the series diverges. I mean, the sequence diverges, right? Okay, so now we've decided it diverges. Okay. Let's look at this one. The sequence made up of the terms n squared over 2 to the power n minus 1. So the denominator is 2 to the power n minus 1. And we want to find the limit as n approaches infinity, okay, of the terms n squared over 2 to the power n minus 1. And notice again, okay, if we look at the limit of the numerator only as n goes to infinity, we get infinity. And if we look at the limit of the denominator alone as n goes to infinity, we get infinity. So once again, we have L'Hopital's rule applying. And so what we need to do then is to apply L'Hopital's rule. We need to find the limit of a new fraction. Now, this isn't a problem for the numerator. If we take the derivative of n squared with respect to n, we would get 2n, wouldn't we? Now the question, though, is what do we get in the denominator when we take the limit of 2 to the n minus 1? Well, what do we get in the denominator when we take the limit of 2 to the n? See, that's kind of like saying f of x is 2 to the x, what's f prime of x? Well, remember how that goes? It's the natural log of the base times 2 to the x power here, okay? Remember that from way back, okay? So the result we get now looks like this, okay? So when we find the derivative of 2 to the n minus 1, we actually get the natural log of 2 times 2 to the x power as our denominator. But, oops, as n goes to infinity. If we look at the numerator now and look at the limit of the numerator, we get infinity again, don't we? And in the, oops, that's a 2 to the n down here. I'm sure you caught me. And if we look at the denominator, because n is going to infinity, 2 to the n goes to infinity, and that constant is not changing anything, so it's the indeterminate form infinity over infinity again. So we could apply L'Hopital's rule. Let's see if it will do any good to apply it again. Well, this time the derivative of 2n with respect to n would just be 2. Now in the denominator, we'll have we're taking the derivative of a constant times 2 to the n power. Well, that's the constant, okay, the constant natural log of 2 times the derivative of 2 to the n. But the derivative of 2 to the n is the natural log of 2 times 2 to the n. So we'll actually have the natural log of 2 squared times 2 to the n. Now, as n goes to infinity, what's going to happen? The numerator is going to stay constant, but the denominator is getting larger and larger and larger. So in this case, the limit is 0. So that tells us that the sequence converges because the limit exists and is finite, and in fact, it converges to 0, or the limit is 0. Okay, let's look at another strange-looking example here. Well, as you see, our next sequence is that we're determined whether it converges or diverges is a sequence of the terms cosine of n over n squared plus 1. For each n, of course, 1, 2, 3, 4, 5, and so on. So we're looking for the limit of the cosine of n over n squared plus 1, and we have to stop and think about this because here is the issue. Of course, that denominator is getting bigger and bigger. And what's happening to the cosine of n as n goes to infinity? Well, the cosine of n is sometimes around 0, sometimes it's a positive number that's less than 1, sometimes it could be 1, but it also could be negative number, but it's never going to be smaller than negative 1 or bigger than positive 1, but it can be anything in between, can it? And so it's going to jump all around. Well, what's going to happen? You say, what's going to happen here? This is a harder question when we start thinking about it. I mean, what is that limit? So here is an example of using, and I'll show you how we use the squeeze theorem. We actually use the squeeze theorem. And I kind of gave a preview to it by the way I described this squeeze theorem. What we can look at is that we know that the cosine of n is always, for any n value, is always between negative 1 and positive 1. Oops, negative 1 and positive 1. Okay? So we know that. Now, to create the term that we have above, we could divide through this inequality by n squared plus 1. So, now, by the way, n squared plus 1 is always going to be a positive number. So when we divide by a positive number, around inequalities, we don't have to change the direction of the inequality. So we're going to divide that -1 by n squared plus 1. Of course, we're going to divide that cosine of n by that n squared plus 1. And of course, we're going to divide that 1 by n squared plus 1. Now, this is kind of like in the squeeze theorem. This is the term a sub n, and this is the term b sub n, and of course, this is the term c sub n. We've got this term squeezed in between two other terms. So the way we'd actually apply this then is to say, okay, well, let's consider the limit of -1 over n squared plus 1 as n goes to infinity. And that's certainly less than or equal to the limit of our sequence, cosine of n over n squared plus 1, as n goes to infinity. And that's certainly less than or equal to the limit of 1, so we've taken the limit all the way through, you see, okay, as n goes to infinity. Now, so we could have done that. Now, in this first limit, of course, we have a negative number each time, because n squared plus 1 is going to always be positive. So we have a negative number each time. And that denominator is getting larger and larger and larger. Although we have a negative number, it's 1 over a increasingly large denominator, unboundedly large. And so the whole fraction is going to 0 as n goes to infinity. And we could do it other ways, but we have recognized that. So the limit of -1 over n squared plus 1 as n goes to infinity is 0. So 0 has got to be less than or equal to the limit that we're looking for. Okay, that's what we're looking for. Now let's go over here. The limit of 1 over n squared plus 1 as n goes to infinity, just like we saw on the other hand, everything's positive this time though. So our limit, if you will, is squeezed between 0 and 0. So our conclusion is that the limit of the cosine of n over n squared plus 1 as n goes to infinity is equal to 0, since it's got to be between 0 and 0. And so that tells us it converges, and it converges to 0, doesn't it? The sequence converges, okay? It's really what I should say. It's not the limit converges, but that's what's going on. We say the sequence converges, and we say it converges to 0. So that's how we actually use the squeeze theorem. Okay, let's look at another one. I've got two more. I've got several more that I want to do. Two more regular sequences and then two special ones. Okay, in this case, let's say number 5. What's the limit? Excuse me, my bad. What are the directions? I've already forgotten the directions. Remember, it's determine if the following sequences converge or diverge, and if the sequence converges, determine its limit. So in this case, the sequence is the a sub n's, okay, the sequence of a sub n's that are of the form 2/3 to the power n. Oh, that's the same form as r to the power n, isn't it? See? Now, we know that sequence converges if r is between -1 and +1, but not ever equal to -1. And this r, for us, is 2/3, isn't it? So it satisfies that. So that tells us, then, remember, we had a theorem that told us, in fact, what it would converge to. Okay, the limit is 0. So again, it converges, and it converges to 0. The sequence converges, and it converges to 0. Okay, next page for problem 6. I'm trying to give you a wide variety here so you can apply different techniques. Ooh, this one looks like there's a bunch of stuff going on here, isn't it? The terms of our sequence are the form 2 to the n times n factorial, all divided by n plus 1 factorial. So let me do a little reminder here. You know, what does factorial mean? For instance, 5 factorial. Well, 5 factorial says we start at the number 5, and then we multiply by the integer that is 1 less than 5, and we multiply by the integer that is 1 less than 4, multiply by the integer that is 1 less than 3, multiply by the integer that is 1 less than 2, until we get to 1. And so that's what 5 factorial would mean. And so in this case, of course, that happens to be what? 20 times 6, that's 120. Okay. Now what we see above, that's just to remind you how we do it. What we see above, notice we've got an n factorial. And we don't really know what n is, but if we were to start calculating, we'd say, okay, start with n. And multiply that with a number that is 1 less than n. Well, a number that's 1 less than n is n subtract 1, isn't it? And then we'd multiply that with a number that's 1 less than it. So we'd take n subtract 1 and subtract 1 from it, and that would be n subtract 2. And we continue, of course, doing that until we get down to a 2 times a 1. Now, importantly here, in this example, in this particular sequence, we also have an n plus 1 factorial. So n plus 1 factorial would be, start out with a number that the factorial is on, n plus 1. Now multiply that with a number that is 1 less than n plus 1. Well, if we take n plus 1 and subtract 1 from it, we're at n. And then we would multiply that by a number that is 1 less than n, and that would be n minus 1. And then we'd multiply that by a number that is 1 less again, that would be n minus 2. And we would continue doing this until we got down to a 2 times a 1. Now the significance here, this is a pretty big deal. We're going to employ this. Look, if we have an n factorial divided by an n plus 1 factorial, since what we really have here, okay, let's look above, we've got this n factorial on top, which is the n times n minus 1 times n minus 2 and so on, and the n plus 1 on bottom, but let's look at the way the n plus 1 on bottom is. Let's say that's n plus 1, and then it's times all of this, isn't it? And all of this is n factorial. So n plus 1 factorial is the same as n plus 1 times n factorial itself. And so that's going to actually reduce, those n factorials are actually going to cancel, and we're going to be left with just 1 over n plus 1. So when we come up here and we look at, so here's what we're trying to do, is to find the limit as n approaches infinity of our terms, and our terms are of this form. And I've kind of ran myself already into trouble here. Maybe we'll come down here. We can simplify that term. We can simplify that expression. N factorial over n plus 1 factorial is the same as 1 over n plus 1. So that expression simplifies to 2 to the nth power over just an n plus 1. Okay, well now, that's an indeterminate form of infinity over infinity, isn't it? The limit of 2 to the n goes to infinity, and the limit of n plus 1 goes to infinity. So we use L'Hopital's rule here. Well, when we use L'Hopital's rule, we have to find the derivative of the numerator. Well, the derivative of the numerator we've already seen is the natural log of the base, which is 2, times 2 to the n power. And the derivative of the denominator, the derivative of n plus 1 with respect to n, is just a 1. And so we end up with the limit as n approaches infinity of just the natural log of 2 times 2 to the n power. Now, we could even go further and say, well, look, natural log of 2 is a constant. We could factor that constant out, and then just worry about finding the limit of 2 to the n as n goes to infinity. But the limit of 2 to the n as n goes to infinity is infinity, isn't it? So we have some constant times something that's getting infinitely large, and that, in other words, that means that this limit is infinity, doesn't it? So what does that tell us? The sequence diverges. If the limit does not exist or is infinite, then the sequence diverges. So in this case, we have a divergent sequence. Okay, as I said, these are the normal types. There's 2 more special sequences that we need to know the limit of. And so I'm going to go through those, and actually we may be able to remember them from when we were in Calculus 1, but let me go through them, and I'll start those on the next page. Well, here are the 2 special sequences, and I'm just looking at the nth term. At number 1, the nth term is 1 plus 1 over n, that whole quantity to the nth power. And in number 2, the nth term is n to a power 1 over n, which is equivalent to the nth power of n. Okay. Now, what we're really interested in doing here, of course, what we want to know is what's the limit of the a sub n's here? What is the limit of 1 plus 1 over n, the quantity to the nth power? Oops. As n goes to infinity. And I'm going to tell you the case here that that's equal to, well, I'll leave it as a surprise, I guess. We'll do it here right now. Now, this is we studied this when you studied L'Hopital's rule. And the way we go about doing this is that we say, okay, and it depends on the book and the teacher, but here's what I'm going to do. I'm going to let's look at this expression, and this is clever, and cleverness comes from experience a lot of times. Let's notice that from a property of logarithms and exponents together, that this expression is actually e to the power of the natural log of 1 plus 1 over n to the power n. Okay. So let me remind you of what that property says. Okay, so that you don't feel like this is just nonsense. There's a property of logarithms that says if you take we'll take some base a, and you raise it to a power that's the logarithm of some expression, but the logarithm is base a, then we get the argument of that logarithm. Now, that's kind of we could probably think that out, but let me do this. Let me do this. Let's call, okay, let's let n be the logarithm of m base a. Okay, let's do that. Now, here's something else. When we take that expression, and we convert it to exponential form, that means we take that base a of the logarithm and we raise it to the power n on the other side, and we get n. Okay, so here's what I'm after. This is going to be like smoke and mirrors. We want to know the value of a to a power that is the log of m base a. And a moment ago, I called the log of m base a lowercase n. And when I changed that form, I found out that a to the power lowercase n is equal to n. I mean, after all, the log of m base a is the exponent we put on a to get n. And we're actually, the log of n base a represents that exponent. Since we're putting it on a, we get n. So if you look back over here, the base of natural log is e, and so we have e to the power log base e of that expression that we have on the left side. And so those two are in fact equal. Now we can go a step further here, because with properties of logarithms, the logarithm of an expression to a power is the power times the logarithm of the expression. So we can actually write this as e to a power that is n, that's the exponent in there, times the natural log of 1 plus 1 over n. Okay. Now here's what we're going to do next. We're going to take the limit. See, here's what we're interested in. This is what we're trying to find, isn't it? The limit of 1 plus 1 over n and actually, I guess hold on just a moment. Okay, so we're trying to find the limit of 1 plus 1 over n to the power n as n goes to infinity. And because that expression is equal to e to this power, that's the same thing as finding the limit as n approaches infinity of e to the power n times natural log of 1 plus 1 over n. Now, of course, the e is a constant. And so the truth is, this is the same thing as e to the power, whatever the limit. I mean, that's what we need to do, is we need to find out what this power is going to. So it would actually be the limit of n times natural log of 1 plus 1 over n as n goes to infinity. Because the limit of e to a power is e to a power that is calculated by taking the limit of that power. So here's what we need to worry about then. So that's we need to know, what is the value of that limit. That's what we need to calculate, so we'll know what that exponent really is. Okay. Okay. Now, if we look at this, notice what indeterminate form this is. This is an indeterminate form. In fact, our original also is an indeterminate form. But here, as n goes to infinity, then the limit of n as n goes to infinity is infinity. What's the limit of natural log of 1 plus 1 over n as n goes to infinity? Well, as n goes to infinity, 1 plus 1 over n goes to 1. And what's the natural log of 1? Well, the natural log of 1 is 0. So this is an indeterminate form, but it's indeterminate form that L'Hopital's rule doesn't apply to. So if you recall, we make a little algebraic magic here, because we can't apply L'Hopital's rule the way this is. But we can algebraically rewrite it. Whoops, that's as n goes to infinity. And so here's what we're going to do. This n that we have in here, this n, we could say, look, if we divide by 1 over n, that's the same thing as multiplying by n, isn't it? So we can, whoops, this is a natural log here. So we can rewrite the fraction that we're taking the limit of. I mean, we can write the expression n times natural log of 1 plus 1 over n as the natural log of 1 plus 1 over n divided by 1 over n. So now what we have, if you look at the limit of that numerator, as we said before, that's 0. And if you look at the limit of the denominator, limit of 1 over n as n goes to infinity, that's 0. So L'Hopital's rule now applies. Okay? So to use L'Hopital's rule, we would have to take the derivative of the numerator and the derivative of the denominator. Well, I hope that you will allow me to tell you what that derivative is without you going through it. Well, you know, I'm stammering here. How do we take the derivative of a natural law? Well, it's 1 over the argument, so it's 1 over 1 plus 1 over n, isn't it? And then we multiply with the derivative of the argument. And the derivative of then 1 plus 1 over n. Well, the derivative of 1 is 0, and the derivative of 1 over n is negative 1 over n squared. And you can verify that without a great deal of difficulty. Now, in the denominator, we have 1 over n. And so we need to multiply, we need to find that derivative. And we just saw above, it says n goes to infinity, I keep forgetting that. And when we find the derivative, the denominator 1 over n, we get negative 1 over n squared. So we have a negative 1 over n squared in both the numerator and the denominator. And so, of course, that will simplify and cancel, and we have nothing more than the limit of 1 over 1 plus 1 over n. Of course, as n goes to infinity, 1 over n is going to 0, and so this limit is 1. Now, it's really easy to forget where we are, but let's go back up here. Let's go back up here, way back up here. We were calculating this limit, okay? And we saw that that expression could be written differently. And so when we were finding the limit of the new equivalent algebraic expression that we have here, then that meant all we really needed to know was the limit of the exponent. And the limit of the exponent is just what we calculated down here. And so the limit of that exponent being 1, then this ends up being e to the first power, or just e. And so that is the big deal here. That's the conclusion, that the limit of 1 plus 1 over n to the power n as n goes to infinity is e. And we will need to use that more and more in this class. Okay, so I'm going to finish off by looking at the limit of the second sequence there, that special sequence, n to the power 1 over n. Well, this is in a sense, it's simpler than what we just did, but it follows the same pattern. We want to know the limit. Oh, and I guess I didn't finish the question on the previous page. So that limit, that sequence converges, and it converged to e. I just didn't say that, did I? But we know the limit was e. Okay, so here we want to know what the limit as n approaches infinity of n to the power 1 over n is. Now, we're going to do the same kind of algebraic magic. We're doing a couple of things. We're doing this a couple of times, and we'll notice in this case that n to the power 1 over n is exactly the same thing as e to a power of the natural log of n to the power 1 over n. See, that's what we just talked about a while ago. Now, because of properties of logarithms, the natural log of n to the power is the power times the natural log. And so this ends up being the limit as n approaches infinity of e to a power that is 1 over n times the natural log of n. Now, it's kind of like, let's look at this kind of as a sidebar. Maybe I should have done this in there. If I wanted to know the limit of 3 to the power 2x plus 1 as x approached 3, what would you do? You would say, oh, well, as x gets close to 3, then that exponent is getting close to 7. And so you'd say, oh, this is 3 to the 7th power, wouldn't you? So what you really ended up doing is just calculating the limit of the exponent, since that base was just constant. As x changed, the base 3 didn't do anything, did it? So that's what we're really doing here, is if we want to know the limit of e to the power, that's just the same thing as e to the power that we calculate by finding the limit of the power. So we're looking now that the result is e to a power that's the limit of 1 over n times the natural log of n. So I'm gonna postpone our work here, and I'm going to come down and say, okay, so it boils down to needing to know what's the limit of 1 over n times the natural log of n, okay, as n goes to infinity. Now, we're kind of in the shape that we were, well, let's see, we were kind of in the shape that we were a while ago. Oh, well, actually, we can rewrite this a little better. Because 1 over n times the natural log of n is the same as the natural log of n all divided by n, isn't it? As n goes to infinity. And so that numerator is going to infinity, and that denominator is going to infinity, and so L'Hopital's rule applies. So to find the limit, we need to find the limit of a new fraction. And what do? We take the derivative of the numerator. Well, the derivative of natural log of n is 1 over n. We take the derivative of the denominator, and the derivative of the denominator is just 1. And so we end up having to deal with the limit as n approaches infinity of just 1 over n, and of course that's 0. So when we come back up here, what we have is e to a power. Now the calculated limit up there we just found is 0. So our original limit that we're interested in is e to 0 or equal to 1. So here's been what we've concluded. 1, the sequence converges. Okay, it converges. Just to make this clear here, because I don't have it on the, we can't see the other page. And the limit of n to the power 1 over n as n approaches infinity is equal to 1. And we'll need that later on as well. Well, this has become long-winded, but I am finished talking about sequences and their limits, whether they converge or diverge. So we'll move on to another section here. But we're finished with this.